So we have this problem in hand. Let me open a whiteboard. Stop share here and let's share the whiteboard here. Let me quickly draw this again. Okay, so this is not possible like this. Let me draw it very quickly now. This is rigidly connected to here. Let's say something like this. It is not exactly this, but so we say that A is equal to A0 B0 plus B0 B plus and then
Pajama was the other way around, I think.
what do you mean other way around? The picture is not the same, but I couldn't draw it exactly the same picture. But this will do for the time being. Let me share the real picture, which I had previously. Stop share. And let's share this one. This was the original picture I had drawn. This one was going upwards, okay? But now I drew it like going down because I couldn't fit it here in my drawing, okay? It is more or less the same thing, okay? The equations will be the same. So. So we have R2 e to the I theta 1, 2 is equal to R1 plus R4 e to the I theta 1, 4 plus S4 3 I e to the I theta 1, 4. This is the last thing we had written. Now this BA has a distance of S4, 3, and its angle is this, which is theta 1, 4 minus 90 degrees, right? There is a difference between this one and that one. Hey, I'm sure, since I cannot copy this, this is a real pain. Let me try to draw it properly. A0, B0 is by 1. So we get the following expression. The angle here, as you see, is theta 1, 4 plus pi over 2. And since that is the case, we can multiply the unit vector by I to get theta 1, 4 plus pi over 2, okay, as our unit vector. So this is where we had stopped the last time. It took a long time to reach there. So we can separate the real and imaginary parts here. R2 cosine theta 1, 2 equals R1 plus R4 cosine 4 plus not plus but minus S34 and S43 are the same thing. Okay, so I'm just using S43 here.
Excuse me, Hujam. Why is the negative sign in the real part right before S43?
Yes, okay. Now there is S43 e to the I theta 1, 4. Now I e to the I theta 1, 4 is I times cosine theta 1/4 plus I sine theta 1/4. And if you multiply this, I times I gives you minus sine theta 1/4 plus I cosine theta 1/4. The real part is this one, and this is the imaginary part. Is this clear? That's why we have the minus sign.
Okay, yeah, thanks. I didn't see the I. I just saw it right now. Thanks.
Okay, so we have the expression. Well, what can we do here? We can do the following. For example, we can get rid of cosine and theta 1/2, get rid of theta 1/2 in the following manner. For example, square each term here and add them. And if you do that, you will get R2 cosine theta 1/2 squared plus R2 squared sine theta 1/2 squared, but cosine squared plus sine squared theta 1/2 will give you a 1. So you will get R squared equals all these things squared. R1 plus R4 cosine theta 1/4 minus S4 3 sine theta 1/4 squared, and it's R2 squared plus R4 sine theta 1/4 plus S4 3 cosine theta 1/4. Now, as you see, squared. In this equation, what is unknown? S4 3 is given. Okay, this was given. Theta 1/4 is unknown. We have to solve for it. So there is only one unknown here, but it's very, very complicated, unfortunately, the equation. We can open it up. And if you open it up, again, you will get some, cosine theta 1/4 squared, theta 1/4 squared, and if you add them to 0, eventually the result will be something like this. Let me write this down. 2R1, R4. This takes some work to do, but eventually you can reach here. Cosine theta 1/4 minus 2 R1 S4 3 sine theta 1/4 equals R2 squared minus R1 squared minus R4 minus S4 3 squared. Well, we get something similar to this Freud-Einstein equation. Let's call this term A. Let's call this term B. And let's call this whole thing C. This A, B, C are known, okay? So we have A cosine theta 1/4 minus or plus, rather B can be like here. This is B, including the minus sign. B sine theta 1/4 equals C. Now, this is a typical equation you encounter in mechanisms, actually. How would you solve this? This is not very easy to solve. It looks not too difficult, but how do you get rid of it? It is a nonlinear equation, cosine and sine terms. There is an analytical solution here, kind of, but it requires some work to do. Let me just open a new page and write this down. A cosine theta 1 plus B. Now, there is you can draw a kind of a triangle here. A right angle triangle, supposedly. Where the sides are A and B. In this case, this distance would be square root of A squared plus B squared. Okay. Now let's call this angle, for some reason, phi. Okay. If you divide this equation by square root of A squared plus B squared, you are going to get A over square root of B squared cosine theta 1/4 plus B over square root of plus B squared cosine theta 1/4 equals C over square root of. Okay, now the trick is the following. Well, look at this triangle, whatever this angle phi is. What is this A over root A squared plus B squared? This is, if you look at that triangle, this is cosine phi. Okay. If you look at that triangle, this is sine phi. And cosine phi cosine theta 1/4 plus sine phi sine theta 1/4 can be written as cosine theta 1/4 minus phi, for example, equals C over square root of A squared plus B squared. Now, ABC, as I have told you, is known. Phi can be determined. So theta 1/4 has a kind of a solution, right? As a matter of fact, we can find these values. For example, A was equal to 2 R1 R4.
Hujam, I have a question.
Yes.
Hujam, what happened to sine phi and sine theta 1/4?
This is a trigonometric identity. Do you remember cosine phi cosine theta 1/4?
Yes, Hujam.
Okay.
Okay.
I call these are cosine and sine phi's, therefore they disappeared. They got into phi. You understand?
Yes, Hujam, thank you.
Okay. Now R1 and R4 were given originally. I don't have them with me now, but eventually this number comes out to be 72. B was minus 2 R1 S43, and this becomes minus 64. R1 was 4, I think. S43 was 4, and 2 is 2, so 64. And C, if you compute it, it is minus 84.95. Okay. And phi can be obtained from tangent inverse of B over A. B and A given, B and A are here. Tangent inverse of minus 64 over 72. which gives you minus 41.6 degrees. Okay. So theta 1,4 therefore is cosine inverse of C over, which is minus 84.25 divided by A squared plus B squared in square root gives you 96.33 minus, or maybe it should be plus 5, but it is, that's a minus, so 41.6 degrees. And the cosine inverse of this thing has two solutions actually. This is equal to plus minus 151 degrees. Both are solutions to this cosine inverse term. Seems. Minus 41.6 degrees. So two solutions are possible. 109.4 degrees is one solution. And the second solution is minus 6 degrees. Let me do the theta 1,4 part. Well, let me go back. From our equation, for example, the real equation, you can easily solve for, from cosine theta 1, 2, you can solve for theta 1, 2, okay? If theta 1,4 is this much, 109, theta 1,2 will be 46.9 degrees. And when theta 1,4 is the other solution, minus 92.6. This is a is this much. Actually, 192.6 degrees is equivalent to 167.4 degrees. We can draw these mechanisms, but let me just a minute. Let me have a look.
Hocam,
Yes.
We found phi as negative, and it says theta 1,4 minus phi. We should write plus 41.6, I guess, to the equation of theta 1,4. Why did we write minus again? Because minus minus plus.
I don't understand. What do you mean?
Hocam, the equation was cos theta 1,4 minus phi. And we found phi as negative value, but we should subtract it again because it was the cos theta minus phi.
Yes.
And minus minus, it should be positive because The value is negative?
No. What happens is the following. You have theta 1,4 is cosine inverse of, rather I should say the following. Just a second. Theta 1,4 minus phi is equal to cosine inverse of C over root A squared plus B squared, right? Then theta 1,4 is cosine inverse something plus phi. Okay.
Okay, I get it. Thank you.
Okay, now these are the possible solutions. One is the regular position of the mechanism. The second is the cross position. If you look at it, the mechanism, this one looks like the second solution. Okay, and the first solution would be this one. This one looks like the thing we have drawn in the previous page. If you want to draw this one, it would look like the following. 46, approximately something like this. And it is 109 degrees. It's possible. This is theta 1, this is theta 1. There is a suppose this is 90 degrees, and then this is another solution, supposedly. Okay, this is theta 1, 2. This is theta 1, 4, and which distance? Well, okay, it doesn't look very correct here. Let me erase this part. It should be a bit like this one. Yes, this is, oh, sorry. This is S3. All right. So the position analysis is, well, it's usually you have to do do some geometrical tricks and have to know some of the geometrical identities in order to solve for the variables. The equations you get are nonlinear. And one problem is you might not even get a solution, a closed form solution for a complex mechanism in the, let's say, in a complex mechanism. There might not be a closed form solution. So you might have to resort to general solution for position analysis might be the numerical methods, okay? I'm not going to go into the details of numerical methods here, but the general technique, the most general technique is to solve for the unknowns in the position analysis using numerical methods. And your book covers that. If you are interested, you can look at it, but I'm not going to go into the details of the numerical methods. Actually, you learn them in the numerical methods class, root solving, and so on. Do you have any questions up to here? Okay. Now, we are, as I said, analyzing the mechanisms. And once you do the position analysis, that is, once you get the possible positions of a mechanism, which is quite important. Here, by the way, once you get the general solution, you can continue this solution and get the mechanism's position for all possible places, for all solutions. For example, for a 4-bar, you can get the all possible values of theta 1,3 and theta 1,4 given for a given theta 1,2. Once you do that, we need to do the velocity and acceleration analysis, which is still kinematics, but analysis, surprisingly, the velocity and acceleration analysis for mechanisms is a little bit, in a way, easier because it is possible to solve for these equations analytically, because the equations we are going to obtain out of velocity and acceleration analysis, as you will see, will be linear. Now, I'm going to first start with doing a little bit of review of dynamics here. As you might remember, we are doing plane motion. That is motion on a surface or a plane. So that if you have an object like this one, this object comes from this position, supposedly being the same object, let's say, comes from here to here. So a line here, AB, in this object comes to A prime, B prime, taking the following path, okay? Now, what are the modes of the plane motion? One mode is the, as you might remember, is the translation, in which the straight lines remain straight. So, for example, if you have an object like this one, and if you have a vector here, this is A, and this is B, This vector, we will call it RB relative to A. Okay. Position of B with respect to A. Here you have A prime. Here you have B prime. And this vector is RB relative to A also. And your path does not have to be a, rectilinear translation. Your path can be like this, for example. But at each point, RB relative to A, both its magnitude and its direction remains constant, okay? So RB relative to A as a vector remains constant here. The orientation of B with respect to A never changes. So an object does a translation when it is moving along a translation path. You can write, for example, the position of B, RB is equal to RA plus RB relative to A. Okay? If you have a coordinate axis somewhere. So this is RA and this is RB. You can write the following. Well, if you take the derivative, RB relative to A as a vector is constant. So you have VB is equal to VA plus nothing, 0. Okay? Because RB relative to A, the derivative is 0. Okay? This is important. Since the vector is a constant, its derivative, vector derivative is 0. And then AB, the second derivative, acceleration. Acceleration of B is equal to A. Now the velocity is tangent to the path, as we know. Let me draw this in another color. This one. So this will be BB. This will be velocities inside the body is all the same, okay? All the points inside the body move with the same velocity. There is no difference. At all points, the velocity is the same. The velocity might be changing over the time, but inside the body, it's all the same. VB and VA, they are the same velocity, okay? This is VB is equal to VA. Okay. VB is equal to VA also. This is translational motion. It can be rectilinear or curvilinear translation, but it's a translation. All the points move with the same velocity and the same acceleration. Okay, this is, we know this. This is the simplest mode of rigid body motion. By the way, we are talking about plane motion of rigid bodies, okay, rigid body motion, not a particle motion. Rigid body means a real body, not just a single point like a particle, okay? Now, the second mode of motion is rotation about a fixed axis. Now, you have an axis that doesn't have to be inside the body, but let's assume that it is. There is a fixed point O here, okay? And your body rotates about this point O. and comes to the following position, let's say. Okay. So A comes, this is the point A, comes to A prime, let's say. How does it move? It moves on a circular path, as you know. Kind of. So this is this vector is RA. Or we can write the following. RA prime vector is equal to RA plus delta RA, which is this vector in between. And let's say that this angle is phi, okay? Now delta RA vector is RA distance times, this is, let's say this is delta phi. Then, if you divide everything by delta t, by the way, this doesn't have to be a vector. Let me erase this part. It's just a scalar equation. So delta RA over delta t is equal to RA delta phi. And when you let delta t go to 0, you have, well, VA equals RA phi dt. And when, if you define omega to be rate of change of angles inside the body, any angle, okay, we can define a quantity called angular velocity of an object. The angular velocity is a property of this body, okay? And actually it is a vector in two-dimensional motion. It is omega times, okay, you can say that the angular velocity vector comes out of the, let's say, the whiteboard. And we can, the correct expression, vectorial expression, velocity of a point is omega crossed with RA. And this is even true for three-dimensional motion. This is an important equation. Okay, so it tells you that if you have an object like this with a fixed point inside or outside it, let's say this is RA. If this is omega, the velocity will be perpendicular to RA and omega. So this will be the VA point. This will be perpendicular. This is a point A. Okay. So let's say that this is angle A right here. This is RA. Yes. VA is perpendicular to RA and omega. Okay. Omega is a vector that comes out of this board, as we see. VA is in the plane. So this point A, is going to trace a circle here. This is, I think, this is just a reminder from dynamics. Okay. And then we will do the accelerations, but we will now at this point introduce the complex numbers and then write this expression I have, this expression in terms of complex numbers and so on. But since it's getting a little bit late, let's take a break at this point and let's continue later. So let's continue here, and I started recording also. Now let's express this in complex numbers. And for that we need a new page. Well, as I said, the position RA of a vector can be written in terms of complex numbers as RA times e to the I theta. Okay, this is the magnitude, this is the direction. If you take the derivative, which you can, of this thing, VA, which is RA dot is equal to, well, we will take the derivative of this now. RA as a vector, well, as a magnitude is constant. This point, this is point A. This distance OA is constant, okay? So this RA doesn't have a derivative, at least not here. But then e to the I theta does have a derivative, okay? So what is that derivative? It is RA times, RA stays there, e to the I theta dot, e to the dot, e to the I theta, which you can write as, if you like, RA times theta, that is omega, okay, angular velocity, rate of change of angles, times e to the I theta. Okay. Yes.
The dot on theta is the first derivative, right?
Yes, that is the first derivative. For example, R dot means dr dt in general. Okay. Newtonian notation. So this is the magnitude for the velocity. And this part is the unit vector again. So magnitude is RA times omega for the velocity. And the unit vector is I times, what is the direction? As we know, we can write multiplying by I basically means rotating a vector. If this is e to the I theta, then this unit vector will be, which is 9, I times e to the I theta. So multiplying by I means rotating 90 degrees counterclockwise, and it's not too hard to show this. E to the I times pi over 2 is cosine pi over 2 plus I sine pi over 2. Now cosine pi over 2 is what? 0. This is I, right? This is 1, sorry. So this is I. E to the I pi over 2 is I. So we can say e to the I pi over 2 times e to the I theta. As we know, this is I, okay? Is, you can write this as e to the I theta plus pi over 2, okay? Which means that I e to the I theta is equal to e to the I theta plus pi over 2. Which means a unit vector, multiplying a unit vector gives you a unit vector that is rotated 90 degrees. So the velocity VA as a vector can be written as RA times omega times I e to the I theta. Okay. In other words, the velocity, if this is RA, VA is perpendicular to RA and omega, as I have told you before. Okay, now one more step is the acceleration. Acceleration is the derivative, vectorial derivative of the velocity which is d by dt of, well, let's use this expression, RA omega I, well, let's use theta dot here, I e to the I theta. It's the same thing. Theta dot and omega are the same, okay? We will use the chain rule. RA is a constant. Theta dot, its derivative is RA theta double dot I e to the I theta, right? Plus, well, we have another, I doesn't have a derivative. E to the I theta derivative is I theta dot here, but you get something like this. RA theta dot I times I theta dot e to the I theta. Which you can write as, well, this is RA theta double dot I e to the I theta minus I times I gives you I squared. I squared is minus 1 minus RA theta dot squared e to the I theta. Or you can say that alpha is angular acceleration theta double dot and omega is theta dot. In which case, this thing can be written as RA alpha I e to the I theta minus RA omega squared e to the. As we know, this is the tangential component of acceleration. Let's use another color. This is the tangential component, and this is the normal component. We are talking about rotation about a fixed point. And let's have another page. So let's say that this is our fixed point. This is RA. Okay. The VA, as we said, is in this direction. Now, acceleration has two components. One is the tangential component, which is like this. Tangential is RA times alpha. And it has a normal component, which is RA times omega squared, and it's directed towards point O. It's point O. And the real acceleration, vectorial acceleration of point A, is this. It's the vectorial addition of tangential and normal components. So this is AA. I'm hitting the top of the screen, so I cannot draw it. So the directions are, as you know, this angle is theta. So this is e to the I theta. Angle is theta. And this is I e to the I theta. And then this is I squared or minus e to the I theta. Okay. The normal component is in the direction of minus e to the I theta, as you see. Okay, so acceleration has, at least in the case of rotation about a fixed point, it has tangential and normal components. Okay, tangential and normal. Now, we talked about translation. We talked about rotation or about a fixed point. Now, the most general thing is the general plane motion. This is just a review of, as you remember, dynamics class with some complex numbers added to it. So we have an object like this one. Now this object comes to something like this, let's say. Something like this. So what we do is, we will say that it is this motion can be decomposed into translation plus rotation. So you can say that, let me do it in another color. Let's suppose that you first translate this like this, supposedly, doesn't look like it, but then about this point you rotate it, okay? So the general plane motion can be expressed as translation and rotation about a fixed point, okay? Right here. This is especially true for, well, infinitesimal motions, okay? Well, for finite motions, this is not really true, but for infinitesimal motions, it is true. It can be shown, but I'm not going to do that. So what we will write is, again, we have a coordinate axis xy. This is RA, etc. This is RB. So you can write RB vector as RA plus RB relative to A. Now, in the translation case, you have VB was equal to VA. Now here we have VB is equal to VA. This is the translation part. And then there is the rotation part, derivative of RB relative to A. If this is about a rotation about a fixed point A, this will be omega crossed with RB relative to A. Okay. So this is a relative motion. This is translation part. This is the rotation part, as you see. We can kind of show this again by drawing the following. Let's say that this is angle 5. Let's say this is let's select our coordinate axis here. This is RA. If I take the derivatives, the relative velocity is going to be VB relative to A. But we can write this as VA. VB relative to A can be written as, let's say, I times and this whole thing will be so VB and VA can also be expressed in complex numbers, but the relative velocity can be written like this in terms of complex numbers as well. Now, we have to do one more thing, the accelerations in the general plane motion.
Could you go back for just 1 second, please?
Yeah, sure.
All right, John, thank you.
Mm-hmm. So we look at the accelerations now. In the general plane motion again, let's say we have a rigid body, AB. This can be, by the way, a link in the mechanism. This is RB relative to A. Well, let's call this something. Let's call it. What can we call it? Let's call it B. Let's say small case B. Okay. You can say that the acceleration of B is equal to AA plus plus AB relative to A. Now, as we know, we can write this as follows. AA plus AB relative to A, the tangential component, plus the normal component, which will be the tangential component, we can write it as B times alpha times I to the E to the I. If this angle is phi, let's say, E to the I phi, plus or minus B omega squared E to the I phi, for example. Okay, tangential and normal components. So if this is, you can write let's say that this is the acceleration of A. In terms of the velocity triangles, it is the following. This is, let's say, this rotates with phi double dot. So you have AB relative to A tangential in this direction. So let's say this is AA. On tip of that, you have it has to be perpendicular to that. Starting from the same point, in that case, this should be, for example, AB. AA plus AB relative to A normal plus AB relative to A tangential is equal to AB, for example, in terms of the velocity polyhedron, okay? It looks like a triangle, but it has to be it has to be a four-sided figure, okay? Now, I'm just doing some kind of a review here. So the acceleration, the general acceleration can be expressed in terms of, again, complex numbers and so on. Now, there is more type of relative motion, which is important for us. Another, let's say, type of now this motion gives rise to the so-called Coriolis acceleration, so we need to look at that. Let's say that we have something like this. Some object sliding over another object. But the important thing is this thing is rotating. This is a 0 fixed point, and this is B. The ground is link 1, this is link 2, and the slider is link 3. 3 is sliding or translating, maybe. With respect to the rotating link 2, okay? The crucial thing is this, that if there is a point B here, if there is a vector RB, this RB, write it here, is a position vector both link 2 and link 3, okay? Their positions is the same, but there is a difference. For B2, well, this R2, this distance RB2, let's say, is constant because its position does not change. But for B3, RB3 is, well, I shouldn't say equal, but is variable because its position changes. B2 and B3 are changes. B2 and B3 are different things, okay? For example, the velocity, if this thing, let's say, has an angle of theta and rotates with omega, okay? Velocity of point B2 will be, well, it will be simply, we are looking at something on link 2, which is this rod which is rotating. So it is, what will that be? R omega. Well, let's call this distance R. R omega times I e to the I theta. This is the velocity of B2. But for B3, it's not the same thing. VB3 will be, well, there is this thing, R omega I e to the I theta, which is VB2. But plus, there is something else. It moves with B2. It moves with link 2, but it moves with respect to link 2 as well. So it is R dot e to the I theta. In a way, I can draw it.
Yeah, we can write R dot as W, right? Or WEI to the power theta.
R dot cannot be written as anything. Let me just draw it here. Just this part. So VB2 is something like this. Okay, it is perpendicular to B2. This is theta. This is rotating with omega. VB2 is like this, but VB3, this is VB2, which is R omega I e to the I theta. I e to the I theta is the direction of B2, and its magnitude is R times omega. This distance is R, let's say. Okay, this distance is R. R omega, and the distance in this direction. But B3, this link has another component, which is the following. It might be going upwards or downwards, I don't know, depending on R dot term. There is this component. B. Well, there's this, which I will call B3 with respect to B2. And VB3, therefore, is the addition of these. This is vectorial addition. So I can write VB3 is equal to VB2 plus VB3 relative to B2. Okay. So this thing I will write it as VB3 relative. Is this clear? You have seen this in dynamics. I'm just kind of making a review here. I think this part is sort of clear. It's not that difficult to understand. Velocity of the slider, we are talking about the velocity of the slider here. The velocity of the slider is simply the velocity of the link 2 on which it slides, which is making a rotation about the fixed point O, plus its relative motion with respect to the slider, with respect to the, the rigid rod on which it slides. Okay, this is what it says. It says the following. Velocity of the slider is equal to velocity of the frame with rotating frame on which it slides plus the sliding motion. Okay, that's what this says. So the velocity part is kind of easy. The more difficult part, as we will see, comes out when we will take the derivative of this. Can I select this? Copy it, maybe. The other. Probably I cannot do it. No, I cannot do it. So let me just write this again. Yeah. Now, The acceleration. We want to find the acceleration of the sliding link. The acceleration AB3 is simply the derivative of this VB3 dot, which we will take the derivative here, chain rule again, R our omega derivative. Well, let's take the derivative of omega first. R alpha I e to the I theta plus R dot omega I e to the I theta plus, not plus, but rather we are taking the derivative with respect to e to the I theta. It becomes R omega squared e to the I theta, right? So triple terms like this. This is the derivative, this parenthesis is the derivative of that term, plus the derivative of this thing, R double dot e to the I theta, plus the derivative R dot omega I e to the I theta. Derivative of e to the I theta. Okay. Let's collect the terms, but we have these two strange terms here, we will see. And they're exactly the same, so we will add them up. Omega, R dot omega I. So AB3 is equal to, what are these? This is acceleration of EQ. This is the tangential component. This is the normal component, normal, okay. Now this is acceleration of B3 relative to B2. Now this is the strange part. This is the Coriolis acceleration. Now the Coriolis acceleration happens or occurs when you have a frame that translates with respect to when you have a object that translates with respect to a rotating frame of reference, and it is expressed in the rotating frame of reference. Let me draw this again. Let's say that we have like this. Components of R double that is in this direction. R omega squared might be in that direction. For example, R alpha is in this direction. These are all velocity components. But the Coriolis acceleration, let me use a different color here. It is this. 2R dot. This is. So the it's in the direction of I_e to the I theta. Now, it's physically hard to imagine, or it's physically hard to give it a meaning. The reason being, it is actually a combination of two different effects. One effect is the well, because of the rotation. The other is because of the elongation of the frame of reference. And it is exactly the same. It gives us exactly the same numerical value. So there is not one physical reason for it, but two physical reasons added up for the Coriolis component. And that's why it is a little bit hard to imagine. Okay. So we have the Coriolis component of acceleration. We have to take it into account when you have a frame that is moving with respect to a rotating frame of reference. For example, the inverted slider crank mechanism. Inverted slider crank, as you might remember, is something like this, okay? Here you have a frame that is moving, well, sliding with respect to a rotating frame of reference. This is the inverted. In those mechanisms, in the acceleration analysis, we encounter the Coriolis term, and we are going to encounter it when we do the analysis. So today I tried to review the velocity and acceleration analysis for rigid bodies. We didn't start mechanisms yet. We will do it the next time. What we did here was basically a review, but it had to be done. And I tried to connect it to complex numbers. Okay. Any questions up to here? Okay. I'm stopping to share them, sharing them. Well, it will be all for today then. Thank you for listening, and let me stop the recording.